Bienvenido a un nuevo contenido de Uninorte Co. No olvides suscribirte a nuestro canal.
Good afternoon. Welcome everyone to a new session of PIA Webinar Series. First, I want to remember that Partículas in the Americas, PIA, is a jointly initiative supported by the Asociación Argentina de Sedimentología, SINSTAD from Mexico, Escuela Politécnica Nacional from Ecuador, Instituto Argentino de Oceanografía, Instituto Geofísico del Perú, Mississippi State University from the United States, Universidad de la República from Uruguay, Universidad Federal do Espírito Santo from Brazil, Universidad del Norte from Colombia, Sequoia Scientific Inc. from United States. Today is the last session of the year. We will come back in February after holidays, but in the meantime, you can visit our webpage and see again the session that we had this year clicking on this option after the description of the webinar that we had this year. Today, we're pleased to present Dr. Susana Binson, who is going to talk about fine sediment in the large Amazon system. Dr. Susana Binson is a water resource engineer from Universidad Nacional del Litoral in Argentina, where started her academic career in fluvial hydraulics. She joined Universidad de la República in Uruguay, doing pioneering numerical modeling of Rio de la Plata. After she moved to Rio de Janeiro for her master and doctoral in coastal engineering, and Professor Ashish Mehta, during her studies at University of Florida, introduced her to cohesive sediment and to the AMASED project, a multidisciplinary study conducted at the Amazon continental shelf. Is professor in coastal engineering at Federal University of Rio de Janeiro since 1982. She started a cohesive sediment dynamics laboratory. She has been working in research and consulting projects in many places on cohesive sediment. A number of master and doctoral students she advised developed their work on Amazon estuary-related subjects. Her talk today is going to give us an overview of this work. We're pleased to introduce you, Susana Binson. Please, Susana, go ahead.
Thank you very much, Camilo, for your introduction. I hope you are seeing my screen. Is everything okay? Can you hear me well? So, I'd like to thank the group of PIA. I'd like to thank Geraldo, Francisco, Yogi for the invitation. It's a pleasure to be here, to be part of this seminar. Actually, it's an honor to share these talks with some prominent researchers we have already on this seminar. So I will give fine sediments in the Amazon system. It's a general title, but I will be referring briefly to the source of fine sediments in this system. I will point the estuary features like tidal propagation, tidal symmetry, salinity front that interact with fine sediments, and then will determine where the fine sediments in suspension is going to be, how it's going to be, and about the mud deposit that we have on the continental shelf. So fine sediment source for the Amazon estuaries, they come from the Andes. You can have here a picture with the main sources, which are what is called the Isaac tributary entering the Brazil borders, let's say that, and Madeira River, maybe the more important tributary for sediments. And you can see that they have their basins ending up in the Andes, starting in the Andes. This is a different picture when you have rivers like the Black River and some other rivers in the lower basin, that they have their basins in the forest with no fine sediments in suspension. So this picture here may be the more spectacular view of the encounter of these two sources for the Amazon River. Amazon in Brazil is called after the join of Black River and Solimões River at this point. So where you can see the white waters that are full of fine sediments and the black waters that have no fine sediment. So in the talk, in the previous talk, Edgardo Latrubesi gave you a very nice introduction of this source and also sinks along the basin of Amazon. I just included here one of the pioneer work by Bob Mead from US. Pointing here, well, there's two main sources, as I said, the Madeira rivers, and here we have different stages of the river and the sediment transport going to the main stem. Here from Madeira, for instance, and Issa, the two main contributors. So if you want to more about this, you may visit Sequoia, the PIA website, and the previous webinar, you can have a nice picture on this. The issue is that we have all this sediment load coming down, all the tributaries and the main stream, and we will find mostly in all the river bottom up to the mouth, we will find sandy bottom. Also, you may see the nice presentation by Jorge Abad from Peru, also in this seminar, the previous one to Edgardo, where you can see how the morphology actually is ruled by the sediment transport in the sandy fractions. So here I just put an illustration of the bed form we have been looking at. This is in this part of the river, the lower part of the Amazon River, where you will find no fine sediments, as I said, all along the river. You may find the fine sediments in the floodplains in the upper part of the river, as Edgardo pointed. In the flood areas, we have huge flood inundation areas where, yes, the fine sediments will get there and will deposit in this part, but not in the main stream. It is all the way long, like you can see in this picture here. The bed low has been estimated by Maxi in about 5 millions of tons per year. But if we look at the fine sediments that arrive to Óbidos, Óbidos is what we consider the last hydrological station. That means this is where the river finish. So if we look at the fine sediments, at the total sediments in Óbidos, we will see that the 90% of the sediments, or more than that, are fine-grained. Fine-grained means silt and clay fraction. So this amount is of the order of the billion of tons per year. So here on the left, on the top and left, you will see the water levels in Óbidos, so changing about 7-8 meters between the low and high waters. And you will see that the fine sediments, which are the most part of the sediment that pass Óbidos here, they are shift by about 3-4 months with the peak of the water discharge. The concentrations of the sediment that arrive to the estuaries varies from 50 milligrams per liter to 250 milligrams per liter, which is not really a high concentration load, but it, of course, because of the large discharge, we have really a huge amount of fine sediments arriving to the estuary. So these things that the river carries to this lower part of the river will meet the tides at the ocean border. So here we have an illustration of the MTU component of the tide, which is the main component in this area. And you can see that this is an area in the north part of Brazil where the tides are the largest. So we have a large amplitude tide at the mouth where this river is discharging. And according to the phase, this tide actually, they propagate more or less perpendicular to the coast. So we have a tide propagating towards the mouth of the river. So as a result, we can define an estuary in several ways. The way I like it better is the estuary is the space where the river and ocean interaction occurs. That means it is not only the mixing zone, which is the more classical definition for estuaries, where this fresh water and the salt water mix, but also where the tidal propagates, and in this case goes to this place here that is the town of Óbidos. So what we are addressing here is the propagation of the tide for the minimum and maximum discharge. So when the minimum discharge, we will see maybe 1 centimeter oscillations in Óbidos due to the tide. And this propagation shift downstream for the maximum flow, many kilometers downstream. So this point to the mouth is about 700 kilometers. And what we have here, more or less at the middle of this extension, this part of the estuary is also called the tidal river. So in this, what we see here in these other marks in red and orange are the tidal reversal, the water reversal. So it is where the flow stops due to the tidal propagation. So this is in the low water goes to this islands, Grupa Island, where basically the lower Amazon branches in 2 main canals, the north one that goes here, and the south one that goes in this way. Actually, the river discharge is not 50-50. It is more or less, well, 40% goes to the north channel and 60% going to the south channel. There is also a connection with this other system. This is called Pará River, where the Amazon also sends some water in that direction. So the fact that we have this reversal in the tide due to the tides, it will be reflecting the sediment transport, of course. So as I said, this is all sediment, all sandy bottoms from Óbidos to the mouth, actually to this place where we are going to refer more in detail, which is we call the mud belt. So what we will see all along these channels are bed forms, basically dunes, like they illustrated here in the left. So from Óbidos to the branching here, we will see more or less the slope of the bottom following the general slope we can see upstream in the lower Amazon River. But at the branching, we will see the loss of transport capacity in the sands, and we will start to accrete and to have another slope almost zero, or much shallower areas in this area. So just after the channel start to open to the ocean, more or less in this area here in front of this island, we will start to see these ebb banks, also sandy, with a high rate of migration and very dynamic, as you may imagine. And after the banks, so then we will start to have the fine sediment being deposited and forming the mud belt, which is the shallowest area in the whole system, which is about 10 meters in the 10 meters depth all along this mud belt. So if we look at how the tides and the discharge of the river and the discharge imposed by the tides along the propagation in this area from the mouth to Obidos, we have a picture like you have here, this tree in the top of this slide. So in this red line is zero discharge. So what you have here in the first picture, so the limit of the figure here is 300,000 cubic meter per second. And what you have here in pink is basically the mean, it is filtered, the tide. So in pink here is basically the river discharge. So a bit downstream of Obido, we start to see the discharge to oscillate along the river discharge as we could expect it. During the low river, we have the tide penetrates longer, as we see before. So we will have a stronger signal in the discharge, the oscillation with the tide, as we see here. So if we move to this area and in the Gurupa Island, as I said, during the low discharge, we will have zero discharge during the low river low stage of the river, like I'm pointing here. So this is somewhere a bit further in the island. But if we move up, this is about halfway of the tidal river. So if we move a bit further, more close, more or less half of the distance with the estuary mouth, we will see now that the discharge imposed by the tide are really impressive. If we think that 300,000 cubic meter per second are impressive for a river, the tide may go up to even larger discharges, especially in these are numerical results. We have some measurements, and we have even larger values of discharge during measurements imposed by the tide. So the tide, as we could expect, the tide is a big driver for anything that may happen in the sediment transport and other process in this scenario. So when we talk about tides, we have to think about asymmetries in the tide. There are many ways to look at it. I'm not going into detail, but we have an oscillatory movement. So that means that to have a residual, to have a transport in one direction, we have to have kind of asymmetry. So this is a map of the vertical asymmetry. So the asymmetry in the water levels, so in the oscillations of the water levels. Yeah. So here is an illustration on the left showing how tide can be positive in the sense that you have a shorter flood and a longer ebb. This is typical in shallow areas, and in many systems you will find this positive asymmetry. One, I would say, emblematic feature of this extreme positive asymmetry in Amazon is the occurrence of tidal bores. This tidal bore is registered in this Araguari River here, somewhere here, where the asymmetry is really really high, with flooding times that goes to a few hours. So this positive asymmetry or negative asymmetry in this case are mostly associated to, which is normally the case as well, to M4, one of the overtides of the main component M2, which in Amazon is quite strong. So we will see in the tidal floods, we will see this flood dominance in the velocity. So here is our measurements in a tidal flood like this. So you will see the water level and the flow velocities being much larger during flood than during ebb in these 2 points. However, in the main channel of the estuary, like here is a north channel, for instance, here is a measurement in this point, P5, before the salinity front. And of course, we have to have all the water coming out from the river that flows mainly during this main channel. So this means that even when you have this positive symmetry in the water level, actually the velocity of the flow will be dominated by ebb, because mainly we have to discharge also the river water. Yeah. So here is a measurement with ADCP from about during in one point, a single point, this P5, yeah, looking at the tidal series, the profiles of velocity along the tidal cycle. Yeah. So you can see it's a strong difference between ebb and flood with ebb dominance. So let's talk a bit about the salinity front. So it is well known, actually, that the salinity front in Amazon River will encounter the fresh water only on the continental shelf. So this is now is the work of Ernesto, his master. What you see here is this transit here in red. Yeah, it is from 0 to 160 kilometers. So we are looking at the bottom salinity front position. In blue is 5 practical unit of salinity, and 30 is red. So if you look at these blue lines here, you can recognize the oscillation of the tide, but mainly you will recognize the cycle of spring and nip tides. So, and you may see the influence of the river discharge, but it is really not that strong. So the variability of this salinity front is explained in first degree by the tides, in second by the winds, and third by the discharge. So this may appear a bit strange, but we have to think that actually the river discharge of Amazon varies between about 100,000 cubic meters per second to 250 cubic meters per second, which means it is 2.53 times. So the variability of the discharge is not that high, 1 point, and the other point is when the discharge of this huge amount of water leave the mouth, it actually will go in a very large area or large cross section. So the salinity front that will happen somewhere here, as I mentioned, with the variability we have seen, this 70, well, this is about 80 kilometer variability is in this green 2 lines. So it is in the scale, it is a small variability of the position. But after the salinity front, we will see the effect of the gravitational circulation, of the effect of the fact that we are these two waters mixing, and we will see this collapse of the suspension, as I will show in the next point. So what happened before the salinity front? So what happened from P1, P2, P3, P4, P5, these points that has been searched for some years ago, it is that we are here going shallower. This is, as you may note here, this is the shallow area I mentioned before where the mud belt occurs. So here is kind of ramp. So the flow accelerates, the velocities are increasing from P1, P3, P5, P7, P6, as you see in these pictures on the left. But if you look at the residual velocities, we will see that we have a decrease in the residual velocity. So actually we have a convergence of the residual currents, which is the driver for fine sediment accumulation. So this is what we will see in the measurements of suspended sediment concentrations. So here we have these lines represent these points again, P1, P2, P3, P4, P5, and P6, that after the yellow one is after the salinity front. And each line is one moment during the tide. So for instance, these blue, these cyan lines, this last one, are all the profiles along the tidal cycle. But what you can see is that in P1, we always we see the concentrations that the river brings, more or less the same concentration you will observe in Obidos. So as far as you move from here to there, these concentrations will increase dramatically, I would say. And this case was about from about 40 to 200 milligrams per liter, but we have observed even up to 500 milligrams per liter before the salinity front. So here are salinity observations. Here is no data for P6, but you can see in P5 that already we find the tip of the salinity front just at this last station. So in P6, where we already have the salinity front, we will see this kind of concentration, suspended concentration profile, and here the sensor just collapsed because the high concentration we will have in the near bottom layers. Just to call your attention that we said before that from P1 to P4, it is absolutely sandy bottom. There is very, very little presence of fine sediment. So actually what we have is kind of pan here, going back and forth, and accumulating sediments that will be start to go to the bottom and to form a mud deposit at the salinity from position. So what is the role of flocculation on this process? We don't have really an answer for that, because we have been done some measurements. Here is the LIST instruments, for instance, and what we can see is consistently during ebbs, we can see larger flock size. So here is one example of measurements during the tidal cycle. And then you see that during ebb, normally the flock size are larger. So we have, if we look at the sediments in the dispersal particle, the single particle size is about the order of 10 microns. But when we can see in situ measurements of the size, we will see 100 or even larger flock size. So there evidence that we have active flocculation even before the salinity front, so in freshwater conditions. We have increasing flock size oceanward direction. So we can see here from P1 to P5, we can observe the increase of the size, which also contribute to the fact that finally we will catch these fine sediments and send to the bottom. Also, a larger flock during ebb, that may indicate the resuspension from the resuspension origin of this recirculation in the vertical dimension of the fine sediments and the flocks that are being recirculated in this area. So we can also see this area, which we call the turbidity maximum, from the satellite images. So this was a bit an effort, because here you see in this graph on the right side, you see the number of images you may have in every month, and because the high nebulosity, many clouds, there are 2 months here that there were no single image available for analysis. But anyway, what is represented here in the central figure is a transect along this again this P1, P3, etc. Is this transect and the reflectance of the surface along. So here is this point. This is from the coast to the ocean direction, and here we have the year. So here is it is June, July, August, September, October, etc. So this time of the year is when we have the higher discharge. So we have this shift of the turbidity maximum a bit more to the ocean than during the low river discharge. So this is an effect. But also it's important to realize that it is during this low river discharge, mostly January, February, when we have the peak on concentration, suspended sediment concentration coming from the river. Also, the satellite images show where we have this peak in the surface. It can be seen at the surface of this higher suspended sediment concentration, but low concentration just after that, due to the fact that we have these sediments depositing and forming this mud deposit that start exactly at this mud belt we are pointing at. Well, this work was also possible because we could calibrate the images, because the high turbidity, we always have problem with these reflectance measurements of the normal algorithm. So this was the work by Bruno, by the way. So we in surface, what we see in the surface, this is now, this is an image, but what we have on the left here actually are the measurements during AMASET. In here we have actually the horizontal fluxes of profiles of fine sediments. So here is one measurement, more or less a point measured during the tidal cycle in a point somewhere here. So here it is where the mud belt is, and here is the other kind of profile similar I've been showing you. Here we have more, the velocity of the flow is accounted for. So this is the concentration multiplied by the velocity, so you can have an idea of the transport. So this is logarithm scale. So if we look at this, if we look at the concentrations on the surface in the plume, we will find something between 1 to 10 milligrams per liter. So it is, we have colors, but we have low concentrations in surface. If we look a bit more at the mouth, these concentrations will be higher, but still the transport, if we look at the lower layers, let's say the first 2 meters, this is 2, 4, 6, 8, 10. So it is about 18 meters here, 12 meters here, depth. So if we look at the first 2 meters next to the bottom, we will find 99.99% of the whole transport of sediment. So so now I just changed the scale here, but this is 10 milligrams per liter roughly in the surface. Here we have 50 to 250 milligrams per liter coming from the river. In this turbidity maximum, we go from 200 to 700 milligrams per liter at the surface, just before the salinity front. As we see at the salinity front, we will have this estuary in circulation, we will have tidal straining, we are going to have other processes that will help for forming actually the mud belt with this area, and also to keep this mud fluid enough to be transported northwest. Well, this is a picture from previous, actually, to AMASET projects. About here in this line, what you have are the sedimentation rates of mud, and also these patches indicate the fluid mud. So we have to think that we have this macro tide, especially in this area is where we have the highest tide in this Malacca Island. So more energy we have to keep the sediments in suspension, more and thicker layers of fluid mud we will find. So this is, this is actually an old picture with the sedimentation rate and also the balance of sediments given by AMASET project that gave you an idea that 20%, 25% of the mud will walk to the Guyanas northwest and will nourish the mud banks we will find in all the Guyana coast. We have some sediments certainly going to the tidal flats, as I show in one of the first pictures. We have this positive asymmetry nourishing the tidal flats continually. But I would like to. We have some canyons where we may expect to have mud going to the continental break, but we have a clear limit here where this mud deposit stopped. And here I come to my last part of my talk, and it is the fact that we have an extensive reef system at the Amazon River mouth. This has been already observed before, but there is a recent paper by a team leader, led by a researcher from our university, but also the people from University in Espírito Santo have been part of the group, and they have been mapping the habitats. So you have here, after more or less the bathymetry of 60 or 70 meters, you will find, well, rhodolites and the reef, which are not, which are out of the mud invasion, it says. The mud just keep this area, which is in terms of habitat is quite smooth, as you can see here in this map. So the last process we will see is the fact that actually at the break, at the continental shelf break, we will have the permanent ocean pycnocline, and there you will have the formation of internal tide. And so this refers to the work of this is 2020, the work of Ernesto. And there is evidence from solitons, for instance, the solitons in the surface, the mark of the solitons in the water surface, but there is also other evidence that the presence of internal waves in these continental shelves are quite strong. So he did actually a numerical modeling study, and he showed that actually the internal waves generated at this signal line and this interface, and the combination with the continental shelf break will give you sediment residual transport, exactly giving a limit in the direction of the coast. Here you have I hope you can see, this is the break, the continental shelf break here. I'm pointing, and you can see an area here that goes about 70 meters depth, where these internal waves are very active, and they give you residual transport exactly in the direction we will expect, in the sense to stop the mud deposit being able to go towards the continental break. So also the tidal straining, which is basically a mixing asymmetry, also driven by the internal tide, will show you the same pictures of residual currents towards the coast up to this limit. So I just point here the limit where we have these conversions of currents that explain why the fine sediments and especially the fluid mud is not able to move forward and then make possible the reef to grow and to be established in these areas. So with this, I go into my concluding remarks. I'd like to say, well, this fine sediment travels 7,000 kilometers to the mouth from the Andes to the estuary. Floodplains, tidal floods, and Pará River are nourished continuously, enlighten their present. However, we don't find fine sediments expressively in the bed of the main streams. Meeting a macrotidal regime at the coast, the far largest river in the world carry about 1 billion tons per year of fine sediments. I would say, I would use this word, surrenders. So after encounter the tides, basically the tides will drive all the process that will help us to understand how the sediment behave. So tidal pumping possibly help by flocculation processes, increases the suspended sediment concentration up to 10 times before the freshwater encounter the salinity front. At the salinity front, actually circulation, tidal straining, and the collapse of turbulence in a feedback process, which has been explored extensively by AMASET project. But then they settle out most of the suspended sediment, forming a huge mud deposit that starts here and goes to the Guyanas. So this mud belt is built and maintained at the mouth with this lower depth. Apparently, in the last 50 years, there's no signs of changes on this mud belt. Well, fine sediments are transported northwest, majority in the first 1-2 meters next to the bottom, reaching the Guyana coast, where the dynamic mud banks can be observed. A large reef system along the continental margin points out the absence of fine sediments, suggesting a mechanism to control this transport, and evidence of solitons in the Amazon continental shelf and numerical modeling studies support the idea that the internal tides are the major mechanism preventing fine sediments to flow offshore, allowing the reef to be established. So here I include the master and PhD doctorate thesis in Amazon subject. I didn't know where so many. So these were my thanks to all of you for your attentions, and I like to dedicate to this teamwork in Amazon subject, students, collaborators, and the memory of Leonardo and Professor Benoit, who were very enthusiastic about all this work we have been doing in this fantastic environment. So thank you very much.
Susana, thank you very much for this nice and comprehensive talk about the Amazon storage dynamics, very illustrative. We have plenty of time for questions. The first question comes from Roberto Fernandez, who says, thanks for the talk, Susana. What factors contribute to the change of coastal morphodynamics toward the southeast? There is quite a change around Maranhão, Piauí, where sand dominates the landscapes.
Maranhão and Maranhão is already far from. Maranhão is also a really macrotide environment, very dynamic as well, and the process there, I would say, quite different in the sense you don't have this huge amount of sediment coming to the coast. You don't have the huge amount of fresh water coming to the coast. So we could point, many other driving mechanism, but yes, this is again is still a macrotide environment with all the consequences you can have with, especially with the asymmetry and what I've been discussing very superficially here. Yeah.
Okay, thanks, Susana. The second question is from Hugo de Oliveira. What are the main environmental impacts of changes in the sediment flows? Increase or decrease?
Yeah, I don't think we have elements to address this question because we don't have records of long records of sediments. We have long records of water levels, 100 years in Óbidos, for instance, but for sediments, there is no such information. So what we could expect, of course, with deforestation is an increase in the sediment load, but if we think that the main source of sediments, as Edgardo explained very nicely in his talk, is the Andes, so I will not say, I will not expect to have changes so visible, let's say, that we can show with the data we have. So we really need to maintain long-term measurements program in all systems, especially in this particular system that is so sensible.
Okay, Susana, thanks. This question comes from Gerardo Perillo. Many thanks, Susana. What is the geomorphologic effect of the mud bank by itself? Does it help the transport towards Guyana?
Yeah, it is interesting because we observe a huge amount of transport, as we have seen in these profiles of fluxes, sediment fluxes, but they will show up at the surface, let's say, only when it make the turn in Guyanas, in the Guyana coast. So the sandbank, the mud banks we see in Guyana, they will. There also the tide is much lower, so the tide decreased dramatically from Amazon to Guyana coast. But then the waves, they start to have a role there for the transport of these mud banks. So these mud banks are mainly driven by the wave action, and they I forgot the rate they move, but they are just walking along the coast, more or less. The axis of the mud banks are more or less perpendicular to the coast, so they walk, along the coast. And the more, I would say, more spectacular effect of these moving banks is when the bank is in front of part of the coast. So it is protecting the coast. So you will see, for instance, the growing of mangroves very rapidly. But as soon as the bank moves away, this coast will start to erode. And this is a cycle that repeat and repeat and repeat. Yeah. It is quite interesting and I would say spectacular effect also of sediments coming from Amazon, this mud bank, dynamic and movement and the impact on the coast.
Okay, thanks, Susana. This question is from Alberto Pedrazani Costa. Susana, have you and your team identified ways to improve safety and efficiency of navigation in the region? It's a difficult question.
Yeah, well, this is, I would say that the safety starts with knowledge. So we really, for instance, the bathymetry, the general bathymetry in Amazon mouth comes from the 70s. Today we have a lot of improvement equipments and it is much easier to make everything, but there is no national effort, let's say that, to make comprehensive studies to measure and to understand the dynamic of the area. So I would say knowledge come first for safety of navigation. But the fact is that the mud bottom for navigation, I'm very fond of that because actually give you much more safety than the sandy bottoms. We have very frequently we have groundings in the sandbanks because of their mobility. There is enough depth, so we have deep channels there, but the sandbanks move and they move the navigation channel. But you have to know, of course, where it is. So since the frequency of the surveys is not, will never be, will never go with the pace of the movement of the banks, you will easily have much more grounding there. But it is good that we have such a tide and such currents that up to now all these ships they move away because they wait for the next tide, etc., and the sand move again and the ship go away. So I think we really need to put the knowledge at the first place for navigation. I would say that. I think is what the academy will be with me on this answer.
Yeah, thank you, Susana. Yeah. This is from Francisco Pedocchi. Hi, Susana. Do you have any comments regarding the effect of waves on the sediment transport in the river mouth?
Well, we don't really have too much information about waves in and how waves may interact, but I would say that the tidal currents we are talking about currents about 2.5 meters per second at the mud belt. So it is probably that the waves are secondary in this dynamics. We are at the equator, so we have very regular wave trains. We have very regular situation, and what we can see is probably it is much more important for the fine sediments and the mud deposit out of the mouth. So beyond the mud belt, which is I think strongly dominated by the tide, I will expect the waves to play a role, especially maintaining this mud fluid and allowing its transport to the Guyanas, exporting mud. So yes.
Okay. Okay. Thanks. I have one question from my own. Have you considered the role of organic matter within your studies of flocculation in the Amazon system?
We have done what we have done. We have done some measurements, which were not, I would say, we did not measure organic matter. We have not so much organic matter in the suspension in general. So was, but we in laboratory, we have been working more extensively on different conditions. Organic matter has not been addressed specifically, especially because our major worry was sediment concentration. We work with sediment from the place, so whatever was there was in the experiment. So we did not create artificially any sample. So I would say I have not too much to add about the impact of organic matter on flocculation. We basically look at the shear stress and concentrations, and then salinity as the three main factors.
Okay, thank you very much, Susana. This one is from Oscar Alvarez. Thanks for the talk. If I understand well, the flux size is higher during ebbs when the current is stronger. The strong current then enhances flux formation and growth instead of destroying them.
Yeah, it can be, but also can be because during ebb we will have much more. We will have resuspension. So this is in laboratory condition we couldn't observe this the increase of size of the flux with the shear stress as we observe in the field. So it could be, but also could be the fact that you are during ebb you're resuspending larger flux that went to the bottom and doing this work. So it's not really clear with the studies we have done up to now. Nice, interesting topic to for a new,
Yeah, definitely.
for a new PhD.
Yeah, you're right. We have another question from Francisco Pedocchi. You mentioned that flocculation starts before the river waters meet the salinity front. Can you comment on what may be driving the flocculation?
I think this, well, the increase in the concentrations is, I think, is the main driver on this. You have much more particles to be together.
Okay. Well, Susana, we want to thank you again for your participation. There is another one. We have the last one is important, is from Jorge Abad. Susana, thanks for the talk. At the river mouth, there are several branches of the Amazon River. Is the vegetation or the deposition of sediments the dominant factor to produce that geomorphology?
Yeah, that I don't know. We have. I don't think. I think the vegetation will play a role, but actually, how it is described in terms of more, let's say, large time scale, it is described like a progradient delta. So we are always adding sediments, and of course the vegetation grows up to after that. So I think the control is this mechanism I show as the flood dominance in the tidal flow, bringing new sediments constantly to the coast. Yeah, and then and then the vegetation will be established very rapidly. We are in the tropical.
Okay, and this is the last one.
Okay.
This is from
all of you.
Patricia Buffon. Dear Susana, thank you for your talk. Greetings for Delft. Will you know if dredging works have been performed in this area?
No. I think maybe the ships are dredging naturally because they pass this mud belt touching the bottom. So maybe some dredging in this sense, but by the propeller of the ship. But there's no, as I said, there is no studies to come with solutions. We are lacking actually a lot of information, not only what happened to the bottom, but also what happened with the water surface, or even how tides behave along the mud belt is still an issue. So, but I think we are walking in the right direction. Alberto Pedrasani is working hard to convince the Navy to go ahead. So probably it is something that can be. It is well possible. I mean, it is easy material. The Amazon mud is have a high content of kaolinite, so it's very soft, navigation friendly. So, but the answer is no. There is no dredging in this area.
Okay, Susana. Well, thank you very much again for this fantastic talk. I think that considering the previous talk from Jorge Abad, Edgardo Laturbes, and with you, we complete an amazing travel around the Amazon system, which is great. By the way, this is the last webinar session of the year. We want to thank you everyone for joining us in this initiative. Please remember to visit our webpage in order to watch all the recordings from Marcelo Garcia, Jorge Abad, Edgardo Laturbes, and Susana as well. And we will come back in February. We are going to expect you by then. So have a good day and happy holidays.
Los siguientes contenidos de Uninorte.co te pueden interesar. No olvides suscribirte a nuestro canal.